Okay, so we're not really going to do the celestial sphere yet. That's coming up in video number 3. What I wanted to do is go back to Orion here, our friend Orion, and talk to you about something known as, it's very exciting, known as angular measure. All right. Now this MP business that you see here, MP1-1, that means more precisely. You notice in the first video it said section 1.3 here. That means that the stuff that I talked about in video 1 came from section 1.3 of your textbook. This information comes out of more precisely, which is like a little sidebar in your textbook. More precisely 1-1. I can't remember what page it's on. No, I don't have it here. I can't remember which page it's on, but it's in the first chapter near the front. More precisely 1-1. That is where you find the written information on angular measure. So I want to say a little bit about what angular measure is. It's actually quite simple. I hope you believe me when we're done with it. Suppose I go out tonight and I look at Orion. Okay. Now it turns out that tonight I won't see Orion because Orion is a winter constellation. But suppose that it's December and I go out and there's Orion. Now some constellations are very small on the sky and some are very big on the sky. And that's what we mean by angular measure. It's how big something looks to you. Right? If I am very far away from a large building, I can hold it between my fingers from my point of view, right? If I'm several miles away from the Bank of America Tower in Midtown Atlanta, right? That's a 1,000-foot building, but I can see it between my two fingers. That's a very small angle. As I get closer to the Bank of America Tower, the angle that it covers gets bigger and bigger and bigger. I can no longer hold it between my fingers. It's a bigger and bigger and bigger angle. So in the world of astronomy, what angular measure means is this. This is a little silly, but this is how I think about it. Suppose I'm looking at Betelgeuse here, and I can't remember the name of that star there, but these two stars, the shoulder stars of Orion. And I want to know what angle is between them. Okay? What I imagine doing is taking two pins, two sticks like this, holding them on my nose and pointing one stick, let me do it this way, one stick toward Betelgeuse, the pink one, the other stick toward the other star, which I can't remember the name of, and look, there's an angle there between the two sticks. Now, if I do the same thing with Betelgeuse and Rigel, okay, it's a bigger angle. That's what we mean by angular measure. There's an angle, a certain angle of separation between these two. It turns out that for these two stars here, Betelgeuse and the other shoulder star, I do it like this. If I go out there and do this with the real constellation, you know, and use my sticks and play my stick nose game like this, and I point one stick, I hold the ends of both sticks to my nose, I point one stick at Betelgeuse, the other stick at the other shoulder star, and I hold up my stick like this, that's about an 8-degree angle. 8-degree angle. So we say that there are 8 degrees between those two stars. If I go the other way, if I go from the top of Orion to the bottom, it turns out my angle comes out to be bigger. It comes out to be something like about 20 degrees. Yeah, it's approximately 20 degrees. So this distance from the top of Orion to the bottom is about 20 degrees. Okay. So if I go out and I point at a star over there and a star over there, that angle could be 90 degrees. It could be something like 45 degrees. It could be a large range of different angles. Okay, so the larger the angular separation, the more distant apart the two stars are in the sky. Okay. Now, degrees are fine. I think we all have some idea of what a degree is, right? A circle, 365 degrees around. Let's draw our axes here and here. So each quadrant, right, that's 90 degrees. 90, 90, and 90. I didn't draw that quite centered, but I think you get the idea. I suspect you do. So 1 degree, I exaggerate the size here. That's 1 degree. There are 360, like a little pie, it's like a little pie piece, like a little slice of pie. I can put 360 of those pie slices around the whole circle. That's what we mean by 1 degree. It's 1/360th of the total pie. But I can slice my pieces even finer. I can take my 1 degree slice of pie and I can break it up into 60 more slices of pie. So 1 degree equals 60 of these smaller pieces, and those smaller pieces are symbolized with a prime and are known as arc minutes. So 1 arc minute is 1/60th of a degree. You can fit 60 arc minutes in a single degree. Now I'm losing my eye. You can't. Too much stuff on the board, right? You can see me now. So there are 60 arc minutes in 1 degree. So all an arc minute is a super small angle. Okay. It's a super small angle. That's all it is. It's 1/60th of a degree. We don't usually think in normal day, in our sort of daily comings and goings about angles less than 1, but there's no reason why you can't slice that angle down into as small an angle as you want. And it turns out that you can slice one arc minute into 60 arc seconds. Get it? Minutes, seconds, it's a factor of 60. 60 seconds in a minute, right? 60 arc seconds in 1 arc minute. So this is 60 arc seconds. And it looks like here I wrote arc minutes like they're 2 separate words, but actually they're 1 word. They're all sort of jammed together. I just didn't have room to write the word minutes over there. So arc seconds is 1 word, and arc minutes is all 1 word. And sometimes they're abbreviated arc min and arc sec. Okay, so 1 arc second is 1/60th of an arc minute, which is 1/3600th of a degree. So there are, I'll sit down here, there are 3,600 arc seconds in 1 degree. So an arc second is a little bitty angle. It's 1/3600th of that 1 degree angle right there. So it's super small. Okay, an arc second is a very small angle. Typically in this class we'll be dealing with with degrees and arc minutes. We will occasionally deal with arc seconds, but with things that are very small, like if we're looking at the size of a certain crater on Mars from the Earth's perspective, that might be down in arc seconds, something like that. To give you a sense of what an arc minute is, I'm going to erase this. It's about to drive me crazy. I don't think I need this circle anymore. I want to be able to see you, you to see me. So, to give you a sense of what, say, a degree looks like on the sky or something like that, the sun, okay, that's the sun. The diameter of the sun is about 1/2 degree. So if I go out with my sticks and play my stick game with the sun, I take one stick and point it toward one side of the sun, and my other stick and point it toward the other side of the sun. That'll be about 1/2 degree. Okay, so that is equal to 30 arc seconds. Okay, the sun is about 30 arc minutes. Pardon me. 1/2 degree is 30 arc minutes. The sun is 30 arc minutes from side to side. And it turns out that the moon is the same size. 1/2 degree, 30 arc minutes. It just worked out that way. The sun's about 400 times bigger than the moon, but it's also 400 times further away. So it turns out, and we'll talk more about eclipses coming up, but it turns out that the sun and the moon are almost exactly the same size as seen from Earth. And it didn't have to be that way, it just worked out. Both of them are 30 arc minutes across, about 1/2 degree across. A little bit more in both cases, 31, 32 arc minutes, but that's about the size. So that'll give you a sense of what 30 arc minutes looks like. Okay, smaller angle. Okay, that's it for video 2. Next up, I promise this time it's coming, the celestial sphere. It's very exciting. Buckle up.